Hi everyone, welcome to the third part of the lecture. And now we're going to see the distinct elements problem. Okay, so, all right, so what is the distinct elements? So now we have an input stream, right? And let's say that these numbers are just bit integers, like positive integers, right? Because it doesn't matter. And they're integers from 0 up to 2 to the b minus 1, right? And let's say that m is 2 to the b, okay? So the idea here is that we want to maintain the current number of distinct elements, d, that we have seen so far, right? So here we want to actually, what we're going to do is we want to output an approximate number, right? So a 1 plus epsilon approximate number, right? So what we will do, so what we will achieve is output a number d tilde such that d tilde is less than or equal than 1 plus epsilon d greater or equal than 1 minus epsilon d with high probability. Okay, so we'll have this parameter epsilon as well. Okay, so we will also have this parameter epsilon, which is our approximate parameter. Okay, and that we can set ourselves, right? All right, so how do we do this? Well, how do we solve this? We're going to use strongly two universal hash function for this. Okay, and why? Because remember, whenever I have something that's much bigger, like you should think of this space, like 0 to the b minus 1, like it's really big, right? It could be as big as the stream itself, right? Like this m could be, so m could be as big as the stream itself, right? So we cannot hope to store like all the numbers that we have seen. So when we have a bigger set, but we have a small space, what is our solution? The first thing that has to come to mind is hashing, right? So what we're going to do is exactly that. We're going to use strongly two universal hash functions, okay? And what's the idea? Well, the idea is that we're going to take a strongly two universal hash function that actually, instead of mapping, which sounds counterintuitive, right? Like instead of mapping 0 to n minus 1 to something smaller, which is what we have, we're actually going to map to something bigger. Okay, and it may sound confusing to you, but it will be quite clear in a bit why we want to do this. Okay, so, and remember, what is the idea? If we're using two universal hash functions or strongly two universal hash functions, why can we do this type of trick, right? What you should be thinking in your head is that, remember, it doesn't take a lot of resources to store the hash function itself. It's very cheap to store a strongly two universal hash function, right? Like it costs very little memory to store it. Does that make sense? So we can store the description to a hash function, which maps to some memory that we don't have access to the full memory. Okay, but the idea is that, well, if I have k distinct elements, right, at least I'll be able to estimate using this hash function. Okay, and all right, so here's the thing. From the hashing lecture, right, we know that if I hash a smaller element to even a bigger size set, with high probability, I have no collisions, right? Because a strongly two universal hash function maps like any element kind of uniformly at random to like the 0 up to m cubed. And we know that this is strongly two universal. So two elements, the only thing that we know is that the probability that two elements get mapped to the same like hash is what? Is exactly 1 over m cubed, right? And how many elements do we have? Like this pairwise, we have m squared pairs, right? So with probability 1 over m, when I pick a strongly universal hash function, I have no collisions, right? So that's from the hashing lecture. So, all right. So we know that if we pick this hash function, which is cheap for us to have, with high probability, we're going to have no collisions. But now you're saying, well, how can we still avoid storing these elements? So here's the idea. Okay, suppose that there are d distinct elements, b1 up to bd. Okay, now if the d hash values, they were evenly distributed in 0 up to m cubed, then we know that the tth smallest hash value should be close to tm cubed over d. Does that make sense? So the idea here is that if, like, let's pick our hash table. So we have the big hash table here, like, and this is the image, right? So I have 0 all the way up to m cubed. Now, if the hashes were evenly distributed, right? So they appear in these like things here, in these entries, right? So these are the entries that the hashed values appear. Well, how many different hashes will I have? Remember, I have d distinct elements. So I only needed to consider the d distinct hash values, right? So if they're evenly distributed, then we know that the tth smallest value would be close to tm cubed over d, because if they're evenly distributed, the first one would appear at m cubed over d, the second one would appear at m cubed, like, times 2 over d, and so on, right? If they were evenly distributed. Does that make sense? Okay, but you may say, well, this is not evenly distributed because they're at random, right? So this is not the same. This is only kind of a wishful thinking. Well, but the idea is that they don't need to be evenly distributed. All we need is that somehow, like, the tth value should be close to like tm cubed over d, right? That's all we need. So we don't need everyone to be evenly distributed to make sure that the tth smallest value should be close to tm cubed over d, right? So the idea is, well, we're going to have all these hashes. And if we know that the tth smallest value is capital T, in this case, that the hash values are evenly distributed, we know that T is approximately tm cubed over d. But now, what do we know? We will know T, because that's what we're assuming. Well, little t is a parameter, so we know little t. M is also a parameter, so we also know M. The only thing we don't know is D, but now we can recover D from little t, M, and T. Does that make sense? So here we recover D. Does that make sense? So that's the idea, right? But of course, like, this is kind of, we have a lot of assumptions here that we kind of need to make formal, right? So this is just the intuition behind the distinct elements, yeah? So how do we make this formal? All right, so here's the algorithm. So the algorithm will be, let's choose a random hash function H from a strongly two universal hash family. Now, for each item in the string, what are we going to do? We're going to compute this hash value of H when evaluated AI. And what is the data structure that we're going to have? The data structure that we're going to have is just a list that stores the T smallest values. Okay, so there's a list of size T. That's our data structure. Okay, and again, T is a parameter that we set, right? So we're going to see how to set T in a little bit. Okay, so all we're doing is whenever a string comes, we compute the hash and we say, is this one of the T smallest elements? Like, smallest hash values we've seen so far. If yes, we put it in our list, right? If not, then we can discard it. Okay, so after all the data has been read, now we're going to set capital T to be the Tth smallest hash value in the data string, right? Which means, like, capital T is just the largest element of the list. Does that make sense? And then what we're going to return is, we're going to return Y, which is like little t m cubed over T. Right? And all we need to prove is that Y is approximately D. Does that make sense? So this is the algorithm. Okay. Perfect. So, all right, now here's the question, right? So what are our space requirements? Let's just kind of cut down this because this is the easy part. Well, we're not going to store the whole hash table, remember? So we only need to store the hash function and t numbers, which are the t smallest values we have seen, right? So how much space does this give? Well, if you remember, well, we're going to store t numbers, right? So these are t numbers in 0 up to m cubed. So this is roughly O of b bits. And hash function h from, well, and remember, this is strongly to universal, right? From 0m to 0m cubed. But if you remember, like, we can store such strongly to universal hash function with O of b bits as well. Right, because we can take, like, let's say, for example, the FP to FP construction, and that's enough, right? So that's certainly enough to store it. Does that make sense? And all I need is like the size of the primes, right? So, all right. So then a hash function costs us O of b bits, and the t numbers, each of the numbers cost O of b bits. So our total space requirement is O of t times b bits, right? So that's the total space requirement. All right. So then now what do we need to do? All we need to do is, well, we need to find a good value for t to have a high probability of success and to have y to be very close to the actual number, right? That's the only parameter that we have to work with, right? So, all right. So how do we do this? Well, here's the theorem. If we set t to be equal to big O of 1 over epsilon squared, we get that y is within the range that we want with constant probability. Does that make sense? So, and this is what we're going to prove now. All right, so how do we prove this, this theorem, right? So let's first prove the upper bound, okay, on the probability. So what's the probability that y is too large? Let's just upper bound this probability, right? So this would be like y too large. We want to show that probability that y is too large is small, right? All right, so what happens here? So if y is larger than 1 plus epsilon times d, right? Remember the formula for y, right? We know that y is this value. Then it means that t will be less than tm cubed over 1 plus epsilon times d, right? Which in particular, if I just use this inequality that 1 over 1 plus epsilon is less than or equal than 1 minus epsilon over 2, right? I get exactly this bound. Okay? But what does this bound mean? This bound means, right? So this bound, like, means that from our elements, from our d elements, our hash function hashed at least t elements, right? It hashed at least t elements in the interval 0, 1 minus epsilon over 2 tm cubed over d. Right? So what it means is that Well, from our D elements, our strongly universal hash function is hashing a lot of them in a really small interval of the whole kind of range that we had, right? And now we're going to show that this cannot happen with high probability, okay? That's the idea, right? So, and the idea is really that, so, and in here, you can see again, like this intuition that why are we using the hashing is because when we hash this way, right, like we have no control over the original string. But if we pick a hash function at random, what happens is that with high probability, this hash function is kind of making the distinct elements in our string kind of random. Now, if I had random elements, then we would expect them to be kind of, you know, with high probability be even distributed, right? You don't expect a lot of them to clump in one part of your range. And now that intuition that we had from the beginning, it turns out that is actually true, right? Like they won't be clumped. Like they cannot all be clumped in a small, like the smallest kind of type of range, right? Like a random function will map them kind of, every range gets like roughly the same number of elements, right? So that's the idea. That's why we had that intuition. All right. So again, so we have at least T hash values that are really small, right? So, all right. So now how do we bound this probability? Well, let's say that a random variable xi is equal to 1 if the hash value of hi is small and 0 otherwise, right? So this is just like the indicator random variable that says, oh, this indicator random variable is 1 if the hash value is too small. Hash value too small and 0 otherwise, right? Now, once we have this random variable, what do? Well, we want to use our concentration inequalities to show that some probability is small, right? So how do we use the concentration inequality? Well, what is the expected value of this xi? The expected value of the xi, because xi is an indicator variable, is just the probability that hi is less than or equal than 1 minus epsilon over 2 times t to the m cubed over d, right? But remember, h is a strongly two universal. Which means that it maps each HAI uniformly random in 0 and m cubed. So this probability is exactly equal to 1 minus epsilon over 2 times t over d. Does that make sense? Now comes the following, right? If we have d distinct elements, what is the expected number of elements with hash value less than or equal to this quantity, small? Well, the expected element is just equal to the sum for I equals to 1 up to d of the expected value of xi, because we have only d distinct elements. But this expectation, as we saw, is exactly, so this is equal to d times 1 minus epsilon over 2 times t over d, and the d's cancel. So then we get less than or equal than t times 1 minus epsilon over 2. Does that make sense? If we have d distinct elements, this is the expected number of elements with this hash value, right? So the nice thing about this is that, well, is independent of d and n, right? Which are the parameters that we cannot control. Does that make sense? So, okay, that's great. Now, if we have this upper bound of the expectation, what can we do? Well, here's the idea, right? So we know now, remember, the expected number of elements with small hash value, we proved that it's less than or equal than t times 1 minus epsilon over 2. But if y is bigger than 1 plus epsilon over d, it means that we have at least t such elements. So there's a gap between the number of elements that we have and the expected number of elements. Does that make sense? Which means that in your head, you should already be thinking, oh, concentration inequality, concentration inequality, right? So now we need to show that this does not happen with high probability, and we're going to use concentration inequality to show that this doesn't happen, right? So, okay, so if we have d distinct elements, let's say that this random variable x is the sum of the indicator variables for each distinct element. We know that the expected value of x is less than or equal than t times 1 minus epsilon over 2, right? So, oops. Okay, so then, so what's the probability that we will see greater or equal than t elements smaller than 1 minus epsilon over 2, like this small quantity, right? So now, well, remember, we have a two strongly universal hash function, right? So remember, we cannot, once you see this, okay, and some people ask me in office hours, right? Once we see this, you may be tempted to use Chernoff. Can I use Chernoff here? The answer is no, right? So cannot use Chernoff. And why is that?
They're only pairwise independent, not
exactly. They're only pairwise independent. Only pairwise independent. They're not fully independent. Okay, so we cannot use Chernoff. But if they're pairwise independent, what is the inequality that we know for pairwise independent random variables? Well, if we have pairwise independence, we have a good control of the variance. So Chebyshev would be good. Chebyshev works for pairwise independent, right? So then we're going to use Chebyshev. And to use Chebyshev, we need a control of the variance. But again, that's easy because now if we have pairwise independence, we have a good control of the variance because the variance of x is equal to the sum of the variances of the xi's, right? And all of these xi's, they're independently distributed. So we just need to compute one of those, right? And then what is the variance of xi? The variance of xi, right? If we just look at the formula, it's equal to E of the expected value of xi squared minus the expected value of xi squared. But this is less than or equal than the expectation of xi. And why is that? Because, well, first of all, this is greater or equal to 0. So we can just set this to 0. And we increase. And the expected value of xi squared is what? Is exactly equal to the expected value of xi for indicator random variables, right? Because xi just takes the value 1 or 0. And we know that 1 squared and 0 squared is equal to 1 or 0. Does that make sense? So the variance of xi is less than or equal than the expectation of xi. Okay, excellent. So now what do we know? And remember, for Chebyshev, we don't need to compute exactly the variance. All we need is like an upper bound of the variance, right? To get a good inequality. So by Chebyshev, what do we have? The probability that x is bigger than t, remember, this is the fact that we have like at least t elements which are really small, right? That's what we're trying to measure, is equal to the probability that x is bigger than t times 1 minus epsilon over 2. So this is exactly like an upper bound. Well, sorry, let me put it like this, like greater than the expected value of x, right? Greater or equal. And then this is the gap. So then if we rearrange this, we can just say, well, this is less than or equal than the probability that x minus the expected value of x is bigger than epsilon times t over 2, which by Chebyshev, this is less than or equal than what? Well, it's less than or equal than the variance of x over epsilon t over 2 squared. So if you rearrange, you get exactly this. But what is the variance of x? Right? We know that the variance of x is equal to d times the variance of xi for any xi And we saw that the variance of xi is less than or equal. So this is d times the expected value of xi. Correct? And now, what is the expected value of xi? Right? Well, but if you remember, d times the expected value of xi is exactly the expected value of x, right? By linearity of expectation. And then the expected value of x, we know that this is less than or equal than t times 1 minus epsilon over 2. So then if we substitute the variance here by t times 1 minus epsilon over 2, we get exactly like less than or equal than 4 over epsilon squared t. Does that make sense? Well, you can even say this is less than or equal to t, right? So and then you get exactly that. Okay, so now we know that the probability that this happens, okay, is less than or equal than 4 times epsilon squared t. Okay, and similarly, right, we can prove the lower bound. Okay, similarly, we can prove that the probability that y is less than 1 minus epsilon times d will also be small. And this is a similar calculation to this previous slide. So I'll leave it as a practice problem for you to complete the proof of these distinct elements. Okay, and yeah, here you just need to replace the 1 minus epsilon by 1 plus epsilon and use Chebyshev again. Okay, so this proves that with high probability. So what did we prove? Right, with this probability, like this is the probability of a bad event happening, right? The first bad event, like y too large compared to d, and the other event is that y is too small, right? So we get that both of these elements, like both of these bad events, have a probability at most 4 over epsilon squared t of happening. Then, well, if we set t, remember, we can set t to be whatever we want. So if we set t to be 24 over epsilon squared, it gives us what? The probability that y is within 1 minus epsilon and 1 plus epsilon times d is greater or equal than 1 minus the sum of the bad events, which is 8 over epsilon squared t, which is greater or equal than 2/3. So with probability 2/3, y will be within the right range. Does that make sense? Okay, great. So then this is the analysis of the distinct elements. Okay, and again, what is the space used? As we said before, like, right, we just need to use like t times b bits. B is log m, and t was O of 1 over epsilon squared. So that's the total space used, right? And again, yeah, this is the breakdown that we talked about before, right? And the running time per operation is also pretty small, right? Because all we need to do is to compute the hash function, right? So all we need to do is to compute the hash function. And update our set. Update our list of size O of 1 over epsilon squared, right? So that's all we need to do. So the running time of each operation is small and the space requirement is small. Yeah. Does that make sense? Okay, great. So then this concludes the, yeah, and if you want to do more optimization, like there's smarter ways of doing this, but we don't care much about this now, right? All right, and now let's see the third main example since we have some time. So, but before that, do you have questions about this part of the distinct elements?